we're going to talk about Spark ML. And before doing that, I'll go into a very quick introduction to Spark itself and its base abstractions. So as Greg mentioned, I'm Reza Zedeh. I'm a technical advisor to Databricks, which is the company that doesn't own Spark, but is commercializing it. And I'm also a consulting professor in the Computational Mathematics Institute at Stanford. The Spark ML library is one of 4 libraries that is built on top of Spark Core. And so this crowd, I think, will care most about Spark ML. So Spark Core is a general distributed computing library. I'll describe the core idea and how you can build on top of it in just 2 slides, because I think a large number of this crowd actually were at a talk I gave at this venue, but at a different time, maybe 3-4 months ago. I'll condense that in the first few slides, and then we'll go into ML. So Spark is made up of Spark Core, which is the basic idea. This is the part that is not changing much anymore, where it's fairly stable code-wise and API-wise. And then what's happening is that there's a large amount of growth in the libraries right now. We're building these out very quickly. And the libraries provided are SQL, Streaming, GraphX, and ML. SQL on top of Spark lets you run SQL queries on your distributed data sets in a cluster. Spark Streaming will let you do micro-batch. If you have a stream of, say, tweets or whatever information, a ticker that is coming in, and you need to perform micro-batch operations on it every, say, half a second or so. That's what Spark Streaming makes easy for you. GraphX will let you take a very large graph and perform operations on it, like PageRank and components, etc. And last but not least is ML, which is actually the most active of the 4 projects. And that's, of course, the machine learning library. So we're going to deep dive into that. And before that, I want to very quickly give you the basic idea of Spark. So how many of you are familiar with MapReduce? Okay. So MapReduce solves a lot of problems with distributed computing. It makes distributed computing easy, so you don't have to deal with fault tolerance. You don't have to deal with writing a different program for every single machine that is involved in your distributed cluster. And it solves a whole lot of other problems too, like shipping your computation to where your data is. And that's just not a feature of MapReduce, it's a feature of data flow programming paradigms. And Spark, in my opinion, is one of the more advanced of these data flow paradigms, and now it's become, people are calling it a successor to Hadoop, but I wouldn't even call it that anymore. It's its own thing. And the basic idea that makes Spark possible is the resilient distributed data set. So you're all familiar with a vector or a list in your favorite programming language, right? You're used to it. You expect any programming language that's sufficiently mature to have a library that will let you put things into a container object and then lets you interact with the items in the container in some way. Spark provides you a distributed container called an RDD. These containers obviously cannot provide all the functionality that a regular vector or a list in a single machine programming language provides you, but it provides you most of the functionality you can expect. Like, for example, you can take 2 of these vectors and intersect them, or you can union them, you can do maps and reduces, and you can do maybe 50 other operations that are all listed on the Spark documentation. And so because you have, and you stop thinking about the world in terms of maps and reduces if you have been, hopefully you haven't been, and so you don't have to shoehorn your algorithm into a map and reduce world or any other kind of world. You just have to shoehorn your algorithm into a much more general idea of, I have vectors that are distributed, I need to redo my algorithm, or I need to think of my algorithm in terms of a vector that's distributed. So this project is open source at Apache, that's why it's not owned by Databricks. Databricks has a product called Databricks Cloud that runs on top, runs Spark internally, and provides an in-browser interface to Spark with a lot of nice plotting and visualization and collaboration tools. So I'm not going to go into that, but at least you know why Databricks cares about Spark so greatly. Most of the committers and the founder of Spark are at Databricks. So this idea of having a vector that is distributed, it's of course not, that idea doesn't have anything to do with any programming language, right? So you expect to have this functionality available in several programming languages, and you do. We do all of our work in Scala, and then we create bindings for Java, Python, and there's a new project that provides bindings for R as well. So I'll be switching back and forth between programming languages just to give you a sense of how they differ in the different programming languages. The key idea after you define RDDs, the key idea that makes them possible in a distributed setting is that they know how to rebuild themselves. RDDs, if a portion of an RDD is destroyed because the machine went down, the recipe for creating the RDD is always saved somewhere, and you don't need to care about the recipes. They're handled for you. The saving and making sure that they're in the right place, and make sure that they're not in the right place, but rather replicated, so that if one machine goes down, you can take it from another. RDDs know how to rebuild themselves, so they're fault tolerant, and that's what you expect from a distributed system. Okay, so this is RDDs, and I'm going to assume that I'm going to build upon them heavily from now on. So I'm going to have this distributed data structure that knows how to rebuild itself. I won't go into any more details about how it's implemented. But if you have a question about RDDs, now is a good time to ask it, because we'll be using them heavily now. Yes?
How many days simultaneously can
Handle? Well, in theory, if it'll slow everything down a lot, but you can have almost all of your nodes go down and come back up. And then you can have it, as long as the driver you'll basically have to restart the computation there. So it's not the case that RDDs magically can save data. They just save the recipe for the data, which means that the computation has to happen again. So there's no number on the number of failures. It's just you have to. The more failures there are, the more work that has to be done. Yes.
If your company has an existing Hadoop infrastructure, then with HDFS, do the RDDs sit on top of HDFS, or do you have to make copies of all the data to bring it into?
So you can create RDDs from data sitting on HDFS. So through one line you say create an RDD from this HDFS file, and then that's it.
Okay, but that's making a duplicate of the data, so you'd have another set of nodes.
No,
and one set of nodes that are Hadoop.
Well, no, not quite. So what happens is an RDD is a sequence of operations that, again, know how to rebuild themselves. At the base of one of these sequences is a pointer to an HDFS file. And then your computation will know that it needs to operate on an HDFS file. And so what happens is the computation gets shipped to the HDFS nodes that are responsible for the parts of your data that they hold. And then the data is actually not sent out or copied. It is acted upon where it is sitting. So there's a tight integration with HDFS. And so there's not a duplication. Okay. So let's, one last question. Is it easy to absolutely. Spark is designed from the ground up to be able to handle files on HDFS and other places. But HDFS, because it's fault resilient in a distributed setting, we absolutely care that it's very easy. Yes. In fact, I'll probably have some examples. Yes.
Is there a good way to create RDD or
I believe so. So there are plugins to you can get RDDs from all kinds of things. You can get it from Cassandra or from local files or from SQL queries and a whole bunch of other places. It's one of the more pluggable places for Spark. Of course, yes. Okay. So those are RDDs, and we're going to use them like crazy and very productively so. So I'm going to give an introduction to MLM with example indications, so you can see what kinds of things you can do out of the box. You don't have to actually build any machine learning algorithms yourself. I'm going to go over the benefits of iteration and how they're especially useful for machine learning, because machine learning builds so heavily on optimization. And then we're going to deep dive into how the singular value decomposition is implemented in Spark, and then also how all-pair similarity is implemented in Spark. Last but not least, I'll go over how you can use ML alongside the other libraries that I mentioned. So I guess I should make sure to keep track of time. That's a lot of stuff. Okay, so MLlib started just a year ago, roughly a year ago, out of the AMP lab at UC Berkeley. And since then, it's become the most popular sub-project. We have more than, I believe, 60 contributors and a lot of different universities, many different companies, and this is one of the most active parts of Spark. And it's because Spark makes it so easy to do machine learning, and you'll see why in a second. So it's very hard to give credit to a single person for ML. This is work that's been done by so many different people. There's maybe 20 different people at Berkeley who started it, and then there's maybe another 3 people at Databricks, and then there's hundreds, maybe probably not hundreds, but at least 60 people outside of both of these places that have been contributing. So it's not one person, and you can't give credit to one person, and it's absolutely an open source effort. So the available algorithms, there are lots. Most of these you're already familiar with. The basic linear models, nonlinear models, regression, clustering, decompositions, and optimizations. These are all at least there in some form, and they're constantly being improved upon. So improved upon usually means that they're being changed so that you can scale them up in all kinds of ways. And more algorithms will be added. People are adding them as we speak. The thing that's missing that I've been getting a lot of requests is our neural networks. So that's coming. And apart from that, actually, I think we have most of the algorithms that people really care about. And of course, there'll be more. So let's see some examples of how to use ML. In here, in the first line, we're creating an RDD from a text file. Okay? So this SC is the Spark context. It's a handle onto the cluster. It's called Spark context, and you'll see it abbreviated as SC. This is the variable name, and it's very common to call your Spark context that. We'll create a data RDD. That means that this is an RDD of type string. RDDs are typed, just like collections in your programming language are typed. So this is going to create an RDD of string out of every single line in this text file. And then we're going to parse that, because every single line in this text file happens to be space separated, and we're going to turn it into doubles, and then we're going to cache. What does cache do? It will take your IDE and distribute it across cluster RAM, which means that if you have, say, a terabyte of RAM across your cluster, which is becoming more and more common, and you happen to have a terabyte of data, you can actually distribute your data such that it's in RAM across the cluster. And then obviously things will move much faster because RAM is a whole lot faster than disk. So here, in this case, and you really want to keep it in RAM when you go over the data many, many times, because reading and writing disk is where the bottlenecks in previous data profiling languages have been. So what we're doing here is we're keeping the RDD in RAM across the cluster, and then we say, okay, k-means on this with 2 clusters and go over the data 20 times. And then that's it. That returns the k-means model, and then we can say compute the cost of this, or take this model and find the associated cluster with a new point. So this is k-means, and the point is, much of the implementations follow this pattern. You call one line to get the model, and then you use the model elsewhere. Another example is PCA. In PCA, the data will be asked to be in matrix form. So a row matrix is made up of a matrix that has its rows chopped up. So if you wanted to represent a matrix in RDD world, you can chop up the matrix in lots of different ways. You could say chop it up by rows, you can chop it up by entries, or by blocks. And in this case, it's by rows. So a row matrix will take the points that have been read over. I don't want to give examples of how to read in points over and over again. And then from that, we compute the principal components, the top 20 of them. And of course, I think you guys are all familiar with PCA because I've seen talks, several mentioned them. But basically, you use these principal vectors to bring down the dimensionality of your data. So let's say you have a data set that is 1,000 dimensions, so maybe 1 trillion points of each 1,000 dimensions, and you want to plot it. So you want to bring it down to 2 dimensions. Well, okay, in this case, it's down to 20 dimensions. So you get the principal components, the top 20 of them, and then you multiply your original data. This is your original data, and you multiply the original data by principal components, and that gives you another row matrix, which is whose rows have the projected lower dimensionality version of your data. And then you can do something like do, say, k-means, or you can do k-means, or, so if you do k-means, at this point you've done spectral clustering, if you've heard this, if you've heard of that algorithm. The alternative is, plot these things in 2 dimensions, or generally the reason I see people do PCA is actually to do k-means right afterwards, so that they have spectral clustering involved. And there's nothing principled about using k-means here. You could use some other clustering. ALS is another algorithm that's available. It's being used at Spotify. There'll be a bunch of talks. There were a bunch of talks by it at Spark Summit. Yes.
ALS stands for
alternating least squares. So a matrix factorization technique that is robust to missing data. So this is one of the approaches that also the Netflix Prize benefited from greatly. It's basically recommender systems. What happens is you have a matrix of most often users and items. Users are in rows, items are in columns, and you're trying to figure out how similar, or how much affinity would a user have for an item. And what happens is you want to learn k-dimensional vectors for both the users and k-dimensional vectors for the items. And then when you want to see how much a user likes an item, you take the dot product of the associated user with the associated item. And then that dot product gives you a score. You use that score to find the highest ranking scores to either recommend or to see how much love there is for between that user and that item. So in this case, we're reading in the text file. We create ratings out of the text file. So this is user's ID, item's ID, and how much they rated it. One line, call ALS. So this is saying use one dimension to approximate the data. Go through the data 20 times and regularize the factors with 0.01 regularization. And then, of course, we can use these model. We can use the model that is returned to predict future effects. That's so. These are examples, and I don't want to take too much time on them. There are a lot of different examples on our website. The Spark code itself comes with a whole lot of examples, and you can run these to see how they work out. Yes. Yeah. I'll get to that. Yeah, I'll go into that. So much of anywhere where we can use accelerated hardware through blocks, we do. So there are lots and lots of places where dot products happen, where matrix multiplications happen. And in those cases, we actually have interfaces through netlib Java and also straight up interfaces through BLAS ourselves. And that's always a necessity for contributions to ML, is that you must you must use as many. And Breeze is often what we use for our linear algebra, but we're moving away from that because we want more control over where hardware acceleration happens. I'll go into this more.
Are there ways handling sparse vectors?
Yes, everything has sparse support. Yeah. Okay, so two large classes of optimization problems humans can solve are complex programs and spectral problems. And in fact, it's rather unfortunate. Outside of these classes, we have trouble solving optimization programs. And what do we mean by that? I mean, it's difficult to provably say you've solved an optimization program unless you're solving one of these two types of programs. And that's sort of difficulties with math, difficulties with NV hardness. It's just the way the world is. And so much of machine learning molds itself around these two types of programs. It's not so much that machine learning dictates what kinds of optimization programs they should use, but rather the other way around. Because these are the two types of optimization programs we can solve, much of the machine learning that you guys use calls one of these two families. And I want to go into these two families and how they're implemented. So this is logistic regression implemented in Spark in, I don't know, 8 lines or so. And this is probably the reason I started contributing to Spark. I've been using MapReduce and so since 2006, and I haven't contributed to any of those until Spark came along around 2011. Here we have fully distributed, fault-tolerant logistic regression. First line simply reads in the data, caches it, so you have distributed graph. Second line is just generating the initial guess for the weights. And by the way, the pink is Python. So this is an example of Python. And then we're going to do gradient descent to optimize the logistic regression loss. So here we have to take every single data point and compute the little loss for it, and this is going to return a vector, and then which is the gradient at that point, and then we sum up the gradients using the summation operator, and then we have now the full gradient, and we subtract it from the current test of the gradient. That's it. That's gradient descent. So these blue operations are Spark operations, which means that they're provided from IDEs, and of course so this is actually being shipped off to the cluster. This data would have been, say, on HDFS. This map operation is shipping off the computation. This computation is being shipped. It is then being evaluated on every machine. Every machine will then compute its own little summation, and then they'll communicate to do the full reduce, and then the full reduce will come into the driver. And that's all hidden from you, and that's how it should be. The result is then subtracted, because that's what gradient descent does, and that's it. So fully distributed, fault-tolerant gradient descent in this many lines. And there's nothing stopping you from changing this into some other fancy update. So if you had
conjugate gradient or something like that.
Yeah, if you had conjugate gradient, you would change this with something else. If you had a different loss function, like the SCM loss, you would replace this loss function with hinge loss. If you had, least squares, you would change it with something else. It's gradient descent. It's distributed gradient descent. Because as long as your loss function splits over your data, which means that it becomes a summation of little terms over your data, then this will work. But this is not that optimized. Even this is wasting a little bit of space. So what's happening is the current guess for the weight vector might be quite large because your model might be quite large. Like say if you have 100 million dimensions that you're trying to run, parameters. If your model is 100 million dimensions, then W is 100 million numbers. And it's being shipped off with every single thread computation that is happening. So what if you had many cores on a single machine? Like you had 30 cores on a single machine, each core would have to get this copy. That's a waste, right? You can just have the current guess for the model available on the machine, and then all the threads can hit the RAM of that machine for the current guess of the model. And so you can do that by a Spark broadcast. That's a little bit advanced usage, but it ends up when you have 30 cores, you end up saving 30 times the space in this case because of the fact that the model can be very large. So that's broadcasting. I'm happy to answer any more questions about that later. It's slightly advanced usage, but you should know about it. So these are convex programs. So convex programs can be optimized with gradient descent. You have some other optimization optimization methods in there too, like LBFGS and stochastic gradient descent. For purposes of demonstration, this is good. PageRank is an example of a spectral program that we can do. So when you do PageRank, every iteration is basically a matrix vector multiply, and many matrix vector multiplies are put together to find the top eigenvector for a matrix, and that's the underlying computation of PageRank. There's nothing stopping you from generalizing that in the same framework to an arbitrary matrix. And from that, you then get, say, PCA, because PCA requires finding the top singular vectors of a matrix. So the example PCA that I showed you, it works by computing an SVD. So in the case of Spark, I showed this in the last talk I gave, so I won't go into too much detail, but basically if you had this on MapReduce, you would have 2 MapReduces per iteration. one, to distribute the current guess for the PageRank across the neighborhood graph, and two, just to take the new guess and annotate the neighborhood graph with that new guess. So two MapReduces push that. The thing is, IDDs know how to partition themselves, and so the second MapReduce of take the new guess for the PageRank and annotate the graph with it becomes unnecessary, because in the previous step you just assigned the machine that was responsible for the node for the contributions of the node, and so the new guess is already where it's supposed to be next to the neighbor's. So you can take that idea and run with it. Then there's nothing stopping you from, and of course iterations are also fast, because as long as the data fits in memory, which is increasingly the case, cluster memory, which is increasingly the case, iterations become fast, and we need to do this many times if we want to do many similar vectors. Okay, so with these two enhancements, one is that iterations are fast, and two, that we can partition the matrix such that where a node knows which page is responsible for. Just those two optimizations bring down iteration time compared to PageRank by almost 10 times, let's say 8 times. So control partitioning here means that nodes, pages that are of the same domain name show up on the same machine. So a machine is responsible for all the pages for a single domain, and because so many links between pages are between domains of the same, so many links between pages are inside the same domain because you link to pages that are related or subpages that are related. That will reduce the amount of communication needed over the network, because the same machine is responsible for handling links that go inside domains. And so this last bar is requiring domain knowledge about your graph. The red bar will work for arbitrary graphs, and you can expect these sorts of things for arbitrary graphs. So this idea generalizes to matrix multiplication. Okay, so you can do matrix multiplication, sparse matrix multiplication, and that opens up all of numerical linear algebra. So as long as you can do matrix multiplication, there's optimization that opens up, there's linear algebra. So we're going to use this idea to go into singular value composition and to see exactly how it's implemented in Spark. So the singular value composition, I saw several people mention it earlier. So I'm guessing everyone knows what the SVD is and does. Who knows what the SVD is?
We had a morning class, about 70 people, on independent component analysis.
That's perfect. So we're going to see how Spark does SVD, and I'm guessing, and I'm going to assume that you know what it is. So Spark actually turns the SVD into two cases. The first case is the tall and skinny matrix. Okay, so if your matrix that you're inputting is tall and skinny, I'm not making this up. This is a technical term. The tall and skinny means that you have a large number of rows and you have few columns. Okay, and what do I mean by few? In this case, I mean less than 1,000. Okay, which is, it happens. You might have a trillion rows and just 1,000 columns, and in this case, you can do SVD very differently than if you had a roughly square matrix. In the other case, the fat and short matrix is it's handled in the same way as the tall and skinny is, because you do the matrix transpose and then you work on that. Okay, so there's only really two cases: the tall and skinny case and the roughly square case. So in the roughly square case, we do something, and then tall, and then the other, yeah. So two cases. We'll go over both, and you don't actually need to care about which case you're in, because you just send in your matrix, and there's logic to decide which of the two it should call. This is the logic. It's basically checking to see if n is the number of columns, k is the number of vectors you're asking for, and there are three different. Well, there are really two different. These two are roughly the same. And this is the distributed one. These are the local ones. There are two variants of the local. I'll explain these such that they merge together. But there's further optimization in the tall and skinny case that you can add about later. So the tall and skinny SVD works like this. You have a matrix A that is m by n. Okay. So that's sort of standard notation. All matrices in the world are m by n. And then you compute A transpose A. What are the dimensions of A transpose A? It's n by n, right? So if n is much larger than n, A transpose A is actually much smaller. Okay? And in the case that it's 1,000, say A transpose, in the case that n is 1,000, then A transpose A is 1,000 by 1,000. And that's way smaller than a trillion by 1,000. So we compute A transpose A, and then it's going to be dense, but that's okay. 1,000 by 1,000, it's a million numbers. I can that even on a single machine. And then there's a very nice relationship between the singular value composition of A and the singular value composition of A transpose A. So this is the singular value composition of A. You write it as U sigma V transpose. U is unitary, sigma is diagonal, V is also unitary. A transpose A, because of the fact that U and V are unitary, its SVD looks a whole lot like the SVD of A, but it's missing U, and it squares the singular values. Okay? Sigma is a diagonal matrix, so when you raise it to a power, it just raises the powers of the diagonal entries. So we're going to compute the singular value composition of A transpose A, and that will get us V, and it will also get us sigma, because we can just square root the singular vectors, values that are coming out of A transpose A. So just these, so that's the first line gets us V, and it gets us the singular values, right? But it doesn't get us U. U is still missing, and U is actually quite large, because the dimensions of U is n by k. It's trillion by k. It's still a lot. You can't do that on a single machine. You can store V on a single machine, right? Because V is n by k. Sigma is k by k. These are both small, assuming k is small. Like if you're asking for 50 singular vectors, it's just fine to have these in memory on a single machine. Because remember, we're going to call it skinny case. U is not okay. You have to distribute this, right? So how do you distribute this? Well, you know V, you know sigma, you know A because that's your data. You know how to invert V because it's unitary. So you can put it on the other side. You can solve it. And then you know how to invert sigma too, because it's diagonal. And these are not expensive operations. This is a transpose, and this is just actual inverse, number. So you can solve for U in a distributed way by simply doing these two operations, and divide by sigma and divide by V. And that's how you get U in a distributed way. So there are two distributed operations that needed to happen. One was to solve for U, and the other one was the computation of A transpose A. So to compute A transpose A, you have to do some math and reduces, and you do that by RDB, so you don't really think about math and reduces. And then the other one is also the same. And we have now, I mean, we do this by just operations that we define on the matrix object. So the row matrix object has a compute Gramian matrix method. And so that gives you A transpose A. It's implemented as efficiently as possible. We do that as part of the library. And then this is also a matrix vector multiply, and again, that's also implemented as methods in row matrix. So we actually implement this algorithm not by thinking about distribution anymore. We just have a distributed matrix and we have. Okay, so that's the tall and skinny case. Any questions about the tall and skinny case? All right, so let's move on to the roughly square case. In the roughly square case, we actually do something quite, I mean, it seems silly at first, but we actually use code from the 70s to compute roughly square SVD. So there's this package called RPack, that has been around since the 70s. It's written in Fortran 77, and it's actually immensely optimized for a single machine. And we're in the distributed computing age now. We have to ditch all of our algorithms and move to distributed versions. But in this case, it's okay. We can actually make do with something that is very mature, very powerful. I shouldn't say powerful, very optimized. That's the key. Very optimized code. The way we distribute code from the 70s in this case is because that code only needs matrix vector multiplies to deal with the underlying matrix. So RPack only needs only interfaces with the matrix by matrix vector multiplies. And the matrix itself is going to be very large, right? It might be 1,000,000 by 1,000,000 with a trillion on zeros. However, when all you only need to do with the matrix is interact with it by matrix vector multiplies, then that's okay, because a matrix vector multiply on a million by million matrix is only a million numbers, right? So we can distribute the multiplies and return the results to our path, which is what we do. So as long as an algorithm only acts on a matrix via matvex, then matrix vector multiplies matvex, then that algorithm can be distributed. At least in the case so that you can handle fairly dense matrices and fairly large matrices. Okay? So how do we do this? Well, there's a JNI interface for our path through the netlib Java package. And then anything that's available in Java is available in Scala. We write Spark in Scala, and that's it. So we have the matvex distributed, we return the results to RPack, and then RPack only actually computes this thing. So it computes Krylov subspaces, which really is a fancy way of saying I need to compute A transpose, A squared, A to the 3, and so on. And that's just fine. We distribute it and return the results, and RPack will do its thing on a single machine because the interface to the matrix only needs matrix.
So are you compute bound or network bound?
I would say we're bound by mostly the fact that now a single dimension of the matrix has to fit in there around some machine. So this will work for matrices that are, say, 100 million by 100 million sparse with, say, a trillion non-zeros. Whether we're network bound or compute bound, I don't know off the bat. Yeah, so on the driver, you would like a lot of memory if you have one of your dimensions being very large. But hopefully, yeah. But you don't need the matrix, which is much larger than, say, 100 million, can exploit a distributed cluster array, which is then much more reasonable. Okay. Any questions about this? So you'll get stragglers if you have these really. I mean, processors are all about the same speed these days, right? Oh, the question was if you have a heterogeneous cluster where you have older processors and newer processors, what kinds of, how do these behave? Well, most CPUs these days are about the same speed. So I wouldn't worry about that. You might run into a cluster where you have varying size RAM available on each machine. And in those cases, you just use the RAM that is possible. So an executor will run on a single machine, and in the executor, you tell it to only use up the RAM that's available. So it's fine in that, but you'll probably get stragglers if you then dish out your work equally. Because it's a slower machine, and you're going to be, if you give computation to a slower machine, it's going to take less. It's going to take more time for it to handle. What you'd like to be able to do is just give it less work in the first place, and I don't believe that's done right now. So like we don't look at the machines and say, okay, this machine is particularly weak. Let's give it a little less data. Most of the time, because clusters are very homogeneous actually. So it's been less of a problem. Actually, we haven't gotten a lot of requests to handle that, but you can handle it yourself. Like it's just not handled automatically. Any other questions? Yes.
I guess for some problems, it's better to go to GPUs with small data that you can all this.
So GPUs like CUDA will let you do some very nice BLAS operations. So for example, there's this thing called NV BLAS, which is NVIDIA's BLAS interface. So BLAS is basically an algebra program, subprograms, and we're actually thinking about replacing some parts of. So we interface with BLAS whenever possible. So we push down to regular BLAS, which is just like CPU and CPU acceleration, CPU hardware acceleration when possible, and then NVIDIA and other well, actually, I don't know about NVIDIA. NVIDIA's CUDA has this replacement for blocks called NV blocks. You can push down to that. We have not yet. And I don't know of any cases where people have done this yet. It will help, yeah, but it's just not, it's unexperimented territory. There's nothing stopping you from putting together a network of machines that have CUDA installed. And actually, Amazon EC2 provides machines that have CUDA. So it's actually a very tempting thing. And a colleague of mine at Stanford is wanting to do this. It's just, it's not the nicest thing in the world to have to deal with such low-level plugging in of bots and native interfaces. That's missing. NetLib Java took that. I mean, the reason I give so much credit to NetLib Java is because they've handled all the native calls, and they compile the Fortran code and all the different architectures that the JVM might run on top of, and then they pick the right one to call depending on which machine you're on. So that's a lot of work. Someone did that, and we give them credit because it's a very reasonable thing to release as a package. So there's nothing stopping you from calling CUDA. It's just not done yet because we haven't had requests. So all pair similarity is the next thing. One last wrong question. Great. Okay. So let's say you have n vectors. Okay. Let's say there's a vector per person in this room, and we're trying to find the most similar vectors. And by similar, I mean cosine similarity similar. So that would require, if you were to do it by brute force, n choose 2, which is quadratic in n handshakes, or rather, n choose 2 cosine similarity computations, right? So this is, I don't know, say 100, 150 people, you would need 150 squared different handshakes or cosine similarity computations to figure, and then you go through and find the most similar pairs. And that's the problem we're trying to solve, because this very often happens with, say, recommender systems or clustering documents by cosine similarity. This sort of thing happens all the time. So we'd like to get away from having to square the number of items that there are, because that's infeasible when, say, you have 10 million items. And you can square 1 million because you get a trillion when you have a really good cluster. If you have a really good cluster, you can handle 1 trillion items in a reasonable amount of time. But say 100 trillion, that's exactly what would happen when you have just 10 million items. You're getting into sketchy territory there, and you just can't. Even if you have a cluster, there's no free lunch. So you need to do something more clever. So what we have in Spark is that you can now call as of 1.2. This is not out yet. This is just merged in. It will be available in Spark 1.2. And the code freeze for Spark 1.2 is in a week, and then there's going to be a month of QA, and then it will be shipped to the vendors like Cloudera, MapR, and Hortonworks, and other wonderful companies that package Spark already with their cluster installations. What we do here is we provide a method in row matrix. So the same matrix that provides you SVD will also give you a method that gives you similar columns by cosine similarity. And the way it does that is by an estimation technique called dim sum, which is dimension independent similarity computation using MapReduce. And here the MapReduce is in the name because it's a MapReduce, not because it needs the MapReduce framework or anything like this. It's just the idea of MapReduce. So in this case, when you have, say, a million columns, you can still use a row matrix because every row will fit in a single machine. A is presumably sparse, and then you'd like to find similar columns in A. And that's actually done by some sampling. And the sampling, what it does intuitively is instead of having everyone shake hands, or instead of looking at every single pair of items, including cosine, and then continuing on, what it does is it has some pre-computation to see who could potentially be similar to each other. So if you have a threshold of, say, 40% similarity, it focuses the computations on those pairs that are above 40% similar. And so the less common the less similar pairs will contribute to less of the computation. And that's done by sampling columns or sampling people who are going to be similar to a lot of different, going to be similar to a lot of other people with lower probability. Okay, let that sink in for a second. People who know a lot of other people are sampled with lower probability. Why? Because they're going to show up. We're going to sample them. They're going to show up so much more often. We can sample them with lower probability. So there's less of a chance of missing them out altogether because they show up all the time. So, and then people who are very reclusive, I guess, and don't have many connections, they're sampled with higher probability so that you make sure you catch whoever they're similar to. And then with that, your computation becomes much more efficient. And of course, I'm not going to expect you to implement this or deal with it in your code. So it's just there as a matrix call. So you load up a row matrix, and it's the same one that you could call compute SVD on, or compute principal component on. And then the same one you can say compute the column with the similar columns, and this will compute it with brute force. So that's the square technique that I mentioned. And if you have little data, that's actually reasonable. You get perfect results then, right? Because if you want absolutely every single similarity score, you just call them similarities, and that will return it to you. And then if you want to scale up to a point where it's not feasible to compute all similarities, you give it a threshold, and then the computation focuses on only those pairs that are most similar to the threshold, and then you can scale up a little bit more.
The threshold on connectivity, it's like how many other people.
It's on cosine similarity, so it's a number between 0 and 1.
But how do you have a threshold on that if you're trying to reduce the computation? It's not compute that for all pairs.
So what happens is you pass in this threshold, say it's 40%, and then the computation only spends time spends a significant amount of time on those pairs that are above 40%. So the whole thing finishes faster because the pairs that are less than 40% similar are neglected. Okay, so those are the deep dives. So we went into fairly deep implementation details. Now we're coming back out. We'll be much more fluffy now, but it's still worth your time. So the future work in ML is all over the place, and largely is governed by how much someone needs something, so that they either contribute it or we realize that the community really needs it, and Databricks or the Spark community won't write it themselves. What's currently happening is LDA for topics is ADMM, which is alternating direction method multipliers for optimization. This is out of Stanford. It's an optimization algorithm that is a little more complicated than gradient descent, but has less communication requirement than gradient descent. So you really have the data just sitting in one place, and there's no communication other than a little bit of the current gas between every round. So so most of the work on Spark is out of Berkeley, unfortunately. I mean, I say this with a heavy heart, but it's changing. So what happens is because Spark is out of Berkeley, a lot of the people there care, and a lot of people there care about distributed computing. That's where most of the work on the distributed computing side of Spark happens. And then now that I'm involved, we're doing more and more on the optimization side of the things that Stanford is good at. Stanford is very good at optimization, and ADMM is actually out of Professor Stephen Boyd's group, and I'm working with him right now to build out ADMM and some other matrix factorization and a bunch of other things on top of Spark. So Stanford is getting on this. Matei, who is the creator of Spark, is now a professor at MIT. Although he's spending his time at Databricks, he will be moving to MIT eventually, and then clearly that will mean that folks at MIT are going to start contributing if they're not already. They're pretty sure they are already. I just came back from a class in Maryland, which was an introduction to Spark. I just came back from it. It was Wednesday. We're going to go to NYU to do the same. Amit Talwalkar is going to be a professor, is at Databricks, is going to be a professor at UCLA. So you can see that academia was starting to battle test their algorithm on top of Spark. And there's a project called Spark Packages where you submit code that is not yet ready for inclusion in core Spark, just so that you can have it out there in the hands of a lot of people. In the same way that R has CRAN, we'll have Spark packages, so that untested code that is perhaps a little bit academic or even not even perfect can be out there in the hands of a lot of people, and I expect academics to be using this quite a bit. And of course, you guys, anyone can submit the Spark packages, and this will be announced very soon. Shangre Tang at Databricks is working on building that. The point I'm making is, we love contributions, whether it be to Spark packages, whether it be to Spark 4. There's a much higher bar of getting stuff into Spark 4. And review things to hell and back, and that's how it should be, given that it's so widely distributed. Last but not least, I'm going to give you some examples of how to use MLlib with the other libraries of Spark. Okay? So as of Spark 1.1, which was released a couple months ago, you can now take Spark streaming and build models in an online fashion. So if you have, say, a classifier where data really only matters in the past 10 minutes or so, you have a ton of data coming in, and then data becomes irrelevant very, very quickly. I don't know, 10 minutes is obviously the example I'm giving, but you want to train very quickly, and you want to have your model that is trained in the past 10 seconds available right now. Okay? So that's what you can do now with MLlib Spark streaming. You start off a model, and then you start off Spark streaming, and the examples just come on in, and whenever you like, you can pick the model that is currently learned out and deal with it. And the model is being trained on the fly, so you're not going to have a delay from when you ask for the model, and not a significant delay, just like a method call. The way to be sitting there, ready to be used. So Spark streaming plays nice with MLlib. We're trying to get streaming k-means in as well. Hopefully it will make it in 1.2, the PR is being worked on right now, but I can't promise that. But it will be certainly in 1.3. Decision trees is a little more difficult to. So all of the linear models you can do this with. You can do this with SVM, least squares, logistic regression, because they all can be trained with stochastic gradient descent, and stochastic gradient descent lends itself nicely to streaming algorithms. However, decision trees, they're not trained with stochastic gradient descent. Actually, decision trees are one of the few optimization algorithms. Decision trees are one of the few models that are trained with neither spectrum methods nor convex programs, because they're not amenable to those. Those are currently not streamed, because the kind of work that would be needed is to, like, say, split up a node or prune it up as a new example comes in, and that sort of thing is missing currently. Okay, so that's MLlib plus Spark streaming. MLlib plus SQL, really, I mean, the world of machine learning and the world of SQL don't overlap that much. But certainly in the case of preparing your data and then running machine learning on it, they do. So in this case, what we're doing is taking a bunch of tweets, looking for their latitude and longitude, and then training k-means to build a model of latitude and longitude. So this would look like it's 2 lines, and then out of 2 lines, you're probably going to get something that looks like the map of the world, because latitude and longitude of people tweet all over the world. If you cluster by that, you're probably going to see just the oceans getting in the way. MLlib plus GraphX, a little bit more complicated. In this case, what we have is a graph, and we'd like to use PageRank as we have a graph, and per node we have features. Okay, so this is per node features, let's say span or not, for every single node in the graph. And what we'd like to do is we'd like to compute PageRank and tack that on as an extra feature, and then run some algorithm from MLlib. Right? So in this case, so let's say this is Twitter, and for each user we have a bunch of features like their last login IP and the number of tweets they've sent in the past day. We want to see if they're spammable or not. So we'd like to compute PageRank on top of that. The way we do it is we have the graph. This is going to call GraphX to get PageRank per vertex. So now we have an RDB that is got the PageRank, and then this is the features for each user that, you know, that I mentioned, the number of tweets, etc. Then we join the two to add PageRank as an extra feature, and then we call reduced regression to train with the additional PageRank feature, and that goes on. So here, I mean, it's very easy to. I feel like this is almost cheating, but I couldn't think of anything better to illustrate the interplay between GraphX and ML. But I mean, this is the sort of thing data scientists do, right? You put together tools to create features, usually. I mean, it's feature engineering is a giant part of data science. And this is an example of where you can use the different libraries together to create a data set. The future of ML is all over, but one of the most important things is getting more numerical linear algebra in there, so that people who want to build their own machine learning algorithms can do so with ease. And you know, the basic building block for machine learning algorithms is numerical linear algebra. So, and optimization comes with that. So what we have right now is we have the different ways you can chop up a matrix. The first way is a coordinate matrix, which means that every single non-zero gets its own entry in an RDB. Row matrix is the one that's most fleshed out. It has all those things like SVD and principal components and similar columns. Block matrix is something that a student of mine is working on right now. Literally right now. You know, I'm waiting for him to send an email. The idea there is that you chunk up your matrix into blocks, dense blocks, so that then if you have matrix vector multiplies or matrix multiplies, when you have two blocks, when you have block matrices, you can then exploit things like block operations. You're not going to, the total amount of computation asymptotically isn't going to change, but it will matter drastically being able to operate on blocks instead of single entries just because of hardware acceleration. And then, you know, you have three different matrices, and you're going to multiply them together, right? Every single pair is going to be a different implementation, because these are all different on the back end, right? So multiplying quarter matrix by row matrix needs an implementation. Row matrix by block matrix as well, and all we choose to pairs here. And the research goal that I want to build out is to make it possible to, this is absolutely not available right now. It's something that is much more researchy, and I hope to be able to do in the next, say, 6 months or 6 years. The idea is you have someone who knows math, say a mechanical engineer who's not the world's best programmer, and they are very used to being able to optimize things in MATLAB or in Mathematica with just almost mathematical notation. They just put in like, I want to minimize the square of x minus y subject, x plus y being 1, and x minus y being greater than or equal to 1. This is the sort of thing an engineer wants to do. And they can. There are a lot of tools to do this on a single machine. CVX is an example of one. And in fact, CVX-Pi is an example of that. CVX runs in MATLAB, CVX-Pi runs in Python. And these optimization algorithms that they run at the end of the day are really only going to need matrix vector multipliers. So if you have a lot of data and you'd like to run optimization on it, but you only want to write this form of the objective, you should be able to back CVX-Pi, which lets you do the parsing of these things and turning them into mapbacks and distribute those mapbacks with Spark, with PySpark, Python version of Spark. And then you have an interface to distributed optimization for someone who doesn't know much about computing. That's a research goal. This is not. I'm not going to give you a date that this is going to be available because we're currently designing. But this is the sort of thing that becomes possible when you have a full programming language at your disposal. And this is actually one of the things that makes Spark different from, say, Hive or Pig or whatever. These are not full programming languages where you have full state maintained between iterations, between computations. It's only possible now that you have full programming language. Okay. So, like I said, Spark started out in a research lab out of Berkeley, and it's now become heavily used by industry. The point is that it started as a research pilot, and it's going to continue benefiting from research across universities. And so, if you have ideas or any implementations that you think are particularly useful for the world and be distributed, please consider adding them to Spark, either as a package or to Spark 4. So feel free to ask me questions about that. And that's it. That's the talk. So any questions? Yes.
Are there any plans for things like location-sensitive hashing or spectral hashing?
So LSH, LSH.
Repeat the question.
Oh, is there any plan for locality-sensitive hashing, or what was the other one?
Spectral hashing.
Spectral hashing. So LSH is a way to. So the similar columns that I mentioned is effectively actually LSH with a communication efficient model. So LSH in some form is in there. Spectral hashing you can probably do already, given that there's the singular value composition, but we don't have plans for making it available as just a single call. It's probably just a few calls for your on your own to call it singular value composition. Yeah, I wouldn't expect it to be very difficult once you just get used to calling SVD. Yes, question. So ALS, identity complexity analysis of the algorithm ALS. So the thing is, ALS optimizes an objective that is not convex. And for objectives that are not convex, the mathematical theory doesn't say anything about the number of iterations convergent. And in fact, there isn't a guarantee that you'll converge to the global optimum either. So mathematicians and people who go to conferences like NIPS and ICML care greatly about, and I go to these, and I care greatly about the complexity in mathematical analysis of these algorithms like ALS. So what happens is we know that ALS doesn't have local minima. It has saddle points that you can get stuck with. We've observed that ALS doesn't on real data do this. And that's the best that we have. The other algorithms, such as Lewis' regression and gradient descent, those are much better understood. And there you're actually guaranteed to converge to global optimum. Sure, yeah. Yeah, but I mean, the number of iterations is the number of times all the machines have to work together to do one iteration, and that's immediately when you go into the amount of time that you have to wait. So the amount of communication needed is really what you care about in a distributed setting that is different from what you would care about in a single machine setting. And there, yeah, we have also looked at it. The current version of ALS does a shuffle per iteration, which means that you do a sort of the data per iteration, and that's found to be a reasonable conclusion to optimize sort quite a bit.
Parallel debugging. So let's say I've done hello world in Spark ML and 2 or 3 programs, and I get stuck on something. When I'm running distributed, if I want to debug it, or I just
so there are many ways.
So
the first thing to do is to go to Spark UI. So whenever you run a Spark program, what happens is there's a console in front of you. It's spitting out stuff. One of the most important lines that you can look for is the URL of the Spark UI, which is a super slick interface that gives you timing information. It gives you information about what's currently running, how many tasks are running, how long they've taken, and actually little code snippets of the operations that induce the run. So usually it's on port 4040. So what happens is if you're running locally, you just go to localhost 4040. If you're running on Amazon EC2 or whatever, look for the line that says Spark UI available at blah. And then if the code also fails, you get the exception there. Very nice way. It's a stack trace, and you also get to see which machine it is on. And then you can also further actually look at the logs. You can also download the extended out and extended there for the machine that failed there. And then you also have just your math driver is outputting a lot of debugging information as it's running, so that it tells you things like, okay, I'm about to broadcast a gigabyte of data, and then, okay, I'm going to a gigabyte of data, it's probably okay or not. Or it will tell you, I'm about to ship off a task, which is serialized computation, and this task is of size, you don't want it to be more than a few kilobytes, because it's computation. Computation is supposed to be straight up code. Sometimes you run the data with that, but you have to be careful, because if your task is too big, just shipping of the computation will take too long. And again, all that information is available in the console. So it's very important to make debugging distributed programs as easy as possible. And try to do that. Most of the work is in Spark UI. Look at Spark UI. I think you'll appreciate it. You appreciate it, and that's where most of the areas will do that. Question.
Are there any plans to have Spark include linear programming or integer programming?
Yes. So linear programming is so like I said, convex programming includes linear programming, and integer programming you probably won't. But there's nothing stopping you from implementing yourself. So once you have a linear program solver, you can discretize. Not discretize. You can say submit the integer valued variables as real values, and you'll get some real number from which you point with the bias for the return from the linear program. That's the standard way of dealing with it. I wouldn't be surprised. So there are a lot of mixed integer programming commercial software kits available, and they are bound by the amount of competition that you can do. The thing is, it's an NP-hard problem. People sell you mixed integer programming software that has no guarantees, but it seems to work really well. And I wouldn't be surprised if someone builds that on top of Spark, so that you can, because they probably don't need much more than maybe start to multiply to even other interfaces. We don't have a plan to add it into Spark for ourselves. I'm betting something. Can you speak up? Yes. So Apache Storm, is there a difference between Storm and Spark? And the answer is yes. So Storm is not meant for a lot of things that I showed you today. For example, it's not the place to do distributed machine learning. It's certainly the place to do real-time streaming. So there's a difference between Spark streaming and Storm in that the micro-batch assumption means that Spark streaming is suitable for streaming scenarios where a latency of, say, 100 milliseconds or half a second is acceptable. Storm is for when you need less latency, say up to, say, 10, 20, 30, 40 milliseconds. And even if you want to go below that, actually, no, I don't know. I take back the part about Storm. I actually don't know what Storm's smallest latency is. Okay, I know that Spark's smallest latency is 500 milliseconds, so you shouldn't be using Spark streaming for lower than that. Storm still runs on the JVM, which means that to get real-time performance, you probably need to move away from JVM as well. So even Storm is not truly real-time. So we've decided that we're going to stick to micro-batch. And micro-batch is going to be 500 millisecond intervals. Storm is slightly lower than that, and we're not going to have a library, etc. It's very, we just have nuts and bolts with how you define the data going through a topology of machines. That's what Storm provides you. And that's very different from an RDP. It's apples and oranges. From a use case, 500 millisecond thing is a good separator. Yes.
Yeah, so if you want to implement complex event processing, then what will be the technology of choice? Is it Spark or Storm?
Like if you want to implement complicated, what exactly?
Complex event processing, like say,
complex event processing. Well, like I said, how much of a latency are you need?
Okay, so if the latency is going to be that.
It's going to matter. Yeah, like I said, 500 milliseconds. If you're okay, if you're say doing tweets, for example, if you want a dashboard that shows the number of tweets or hashtags about a particular thing, or if you want a dashboard that shows how many sales you've had in the past minutes or hour, or if you have a dashboard that somehow monitors the health of your system, it's probably okay to have half a second delay. It's absolutely. But then if you have something that is like high frequency trading, then even Storm is not the right thing to use because it's too. It's in the JVM and the delay there is too much.
Yeah, that was the next question. Like, if there is some aspect of real-time learning need to be done, so is Spark the better technology than Storm?
Again, it depends on the latency, but if the latency is okay, if you're okay to learn once a second, Then absolutely, because we have an LLM that learns a model on the fly from data coming in by on the fly per second. And then it's just a few lines to get your streaming machine learning setup going. Whereas it's a whole other different stuff. Yes? One of the goals of resource management is to use the cluster, of course.
For batch and real time using. So do you see the path dedicated cluster, or you can use it with batch? What do you think would be?
There are many ways to run Spark on top of a cluster. You can run it with the cluster manager that pretty much any, so clusters come in all kinds of forms. Right now we support a cluster manager that is, we support yarn, which is runs on top of, and we install it, it's installed yarn. Also mesos. And also there's a standalone Spark node where you can just run with nothing but the cluster manager, just run straight up Spark. If you run with the cluster managers, you get high availability for the master. So Spark provides fault tolerance if the workers go down, and then if you run on a cluster manager, even the master can go down, and it's okay. Spark runs on pretty much any cluster. I mean, most deployments already actually have it installed. Like if you have Cloud AR5, just go into some machine and run the Spark shell, and it's already there. I'm seeing this happen more and more. People ask me, how do I install Spark? I'm like, you sure it's not there already? Many vendors who install clusters for people just install Spark as well. And if that's become less and less of an issue.
Yeah, okay. Just wanted to see if we can postpone questions. If you'd like to propose a session later on, we can continue the dialogue on Spark.
Sure, yeah. Sure.
I just wanted to start off pretty.
I mean, I'm available for questions until lunch or so I have to leave around 2. But I'll be available before then.
Okay. Thank you.